similarity. Here, I've been able to distinguish between self-similarity, which is what I think you would need to demonstrate the log law, and also Townsend's outer layer similarity. So, really following on nicely from what Bill was talking about, we want to know whether the roughness leaves its footprints as it gets to the outer layer. And by inference, one might therefore ask questions about Townsend's outer layer similarity. And sorry about that. And really, our starting point is Javier's review a few years ago, where basically, if the roughness height is less than 2.5%, then we would expect similarity, outer similarity to be observed. So what we're going to do is actually put in some really quite large roughness. So we're actually going to start with a K upon H. H is the duct height with 4%, and then go up to about 8%. And then really look at how things shape up in the flow. But what I really want to get across is the difference, or our perception of the difference between self-similarity of the log law and Townsend outer layer similarity. And I would suggest that this is actually a stronger requirement than Townsend outer layer similarity. So this is a channel. H is the half height. So we're doing measurements at about 128 half heights. It's fully developed for the rough cases. And the RE tau is in excess of 5,500 and goes up to as much as 7,500. The aspect ratio here is 15, and we get the skin friction from the linear pressure drop. And our estimate on the error in U tau is roughly 3%. These are the roughnesses. Here's our benchmark for smooth. We start off with a grit roughness. So this is isotropic. It's really high-grade abrasive paper. It's isotropic. These are the distributions of the height. You can see it's strongly non-Gaussian. It's got a large positive tail to the distribution. And then we have this rather, I'm calling it a pathological roughness, because it's not neither K-type nor is it D-type. I almost like to call it 2.5-dimensional mesh. And that's because really the roughness is made up of this sort of diamond pattern imprint. So this is the spike that you see here on the distribution, but you can see also that it's got the span-wise scale associated with it as well as the length scale. And so in terms of dimensions, we're actually going to have roughness heights or maximum roughness heights of 2 millimeters and 4 millimeters. And so this one's isotropic, the mesh is not obviously isotropic. I'm going to call it a 2.5-dimensional roughness. That's pretty much it. I suppose an unfortunate consequence really of doing measurements on the rough surfaces that L plus of hot wire resolution is always going to be pretty difficult, but we're operating around now plus of about 50. But I think that's okay. We're actually going to focus on turbulence that's some way away from the surface. So these are the test cases. 3 Reynolds numbers for each of the grit and mesh cases. And remember that in a fully developed flow, the roughness is quadratic. In other words, the roughness goes as the area. So that biases our estimate of K plus towards the larger roughness elements, and that's just a way of gauging what the roughness is actually going to be. So for K U tor upon nu here, I'm simply going to take K plus, simply because it's an area relationship in the first place, and in the second place, Holbrook actually told us something about shielding the smaller elements by the larger elements. So that's another reason for basing K plus upon the largest roughness height that we've got. So this is our mean velocity distribution plotted on viscous scales, and I'll say a bit more about the roughness offset that Olga introduced us to just now. Basically, what you can see is that the Harman roughness function increases with the value of K plus. So we come down to here we come down to the grit data, and then we go down to the mesh data. So the roughness offset function, in the case of the grit, delta U plus is about 11 or 12, and then when we get onto the mesh, it goes up to about 15 and 16, so it's large roughness. And this is our reference data for smooth case, and that's our log law. Now, what we've got is a channel, so we can get the friction velocity, and we're actually going to go and choose a value of kappa. And I take kappa equals 0.41. And what I'm about to say, generally the conclusions are not changed by going to a kappa of either 0.4 or even 0.42. Things don't really change that much. Comparison, I put on some of the data from Hilbert's group, Ollie Martin Ruffin. These are his data, so it's actually a very similar experiment. We're in the same sort of ballpark. Now, this is where the fun starts. We begin to see really. What we do is actually represent the log law in a meteorological format. So actually what we do is absorb the absolute constant as the log law function. We fix kappa, remember? And therefore we have two free constants. One, d, is the roughness offset, the other one is the roughness length scale, y naught. So we actually do a two-parameter fit, and those come out of the fit, out of the fit to these data. I'll confess straight away and say that's actually quite a black art. But roughly, D for the mesh has a value of about 0.13 millimetre, and in the case of the grit, sorry, in the case of the mesh, it's 0.43 millimetres, so it's a small offset. So from now on, I'm actually going to refer to y naught as our inner length scale, and obviously the outer length scale is h. So that's how we do it. First thing, on the previous... Yes, of course, yes. So roughly, the higher the roughness height. If you reckon on the weight function with a smooth case, in roughly about 2.6, something like this, you can see straight away that the weight strength has decreased from the smooth case to this for the grit, and then subsequently it's actually reduced even further on the mesh roughness. So there is an outer layer effect as far as that measure goes. Now what we're going to do is start thinking about similarity in the mean velocity profile. So what we want is simultaneous collapse on inner scales as well as outer scales. And by I, no more, what we've deduced is that we get collapse of these data for values on this x-axis here between 50 and 30. So the question is whether we can actually get simultaneous collapse on outer scales. These are the same data on outer scales, so now we've got the velocity defect scale as y minus d by h. Kappa remains the same, this is just the log function with the velocity deficit. And what we can do is keep the absolute constant free and then simply move the log law up and down and see if we get collapse. So this is the log law for the smooth and red, and that looks all pretty hunky-dory. What we can also do is to do the same thing for the grit. And there are a lot of data points on here, and I'm going to take some of them off in a minute. But roughly what you can see here is that the grit actually collapse along this, a straight line, so with kappa minus 1. And these are the mesh data. They look rather peculiar. If we look at the grit, then in terms of expecting inner collapse between 15 and 30, these are the corresponding values for the x-axis on outer scaling. In other words, again by I, these data will also get a simultaneous collapse on both inner and outer variables. Mesh looks a bit more problematical, so let's have a look at that in a bit more detail. We're going to take away some of the data points. Again, by I, what we're suggesting is that actually, for the mesh, the data collapse for a y upon h bigger than about 0.3. And then you ask yourself, well, what's the mesh actually doing? And what we're going to do here is actually then think about the spanwise location of the probe. So far, all the measurements that I've shown you have been taken at the trough, in other words, at the centre of this diamond pattern. So the obvious question is how do the velocity profiles relate when you take them either at the crest or you take some sort of spanwise average of these two positions. Turns out the profiles become spanwise homogeneous for y upon h bigger than about 0.08. So doing any curve fitting below that value is clearly not sensible. And what we're suggesting is that on this deficit plot here, the profiles collapse for a y upon h bigger than about 0.3. So then the question is, where is the corresponding collapse on inner variables? Well, it's there. So we've got collapse on outer variables, we've got collapse on inner variables, but in y space those two are not coincident, they don't overlap. Therefore, we have not been able to demonstrate self-similarity with the velocity profile. Going to the second order moment, the mesh and the grit effectively look like this. Not an awful lot to say, really. I'm not going to really want to go too far close to the wall simply because hot wire resolution is an issue. But you can see how U prime is attenuated by the effect of the roughness, and that's pretty standard. Now this is a complicated plot. Same data, but plotted on outer variables, y upon h. And let's first of all start off with Javier's review. We've sort of taken that as our sort of starting point, our benchmark. And this yellow line here is simply a best fit through his data. And those are for data up to Nari tab about 6,000. What we've also put on are some of Buckin's data. And we get this rather strange behaviour where some collapse onto our data and some actually collapse onto Javier's review data. The distinction seems to be a question of the Reynolds number. And our data for an RE tau bigger than about 5,000 actually fall onto this RE tau less than 1,200. So I'm not quite sure what's going on there, but I'm sure Olga and I can sort it out. Triple products. Skewness, flatness, these actually collapse. The flatness, I suppose, obviously being an even order moment, actually collapses rather better. But basically, these collapse on Y and U2 really quite well in the outer layer. And that's despite the fact that the weight strengths.
We're actually normalizing with U tau?
Oh, sorry, yes, sorry. Yeah, they're U over U tau, so they're not skewed to space. So, third order and fourth order products on outer variables, Y upon H. Collapse for third order bigger than 0.6, Y upon H, and fourth order for Y upon H bigger than 3. So, what we're beginning to see is some differences in the way in which we assess the influence of the roughness on the outer region. And the wake strength, it basically decreases as you increase the size of the roughness. And we're also fairly confident that really quite persistently, Townsend's outer scaling actually works really quite well. But then if you think about it, well, the whole motion, irrespective of the fact that you get a normal pressure gradient, all the motion is actually geared to a streamwise pressure gradient. So perhaps, and that's directly proportional to the shear stress, so perhaps it's not surprising that certainly for an internal flow that Townsend's scaling is actually really persistent. But really, I think our most important result is simply that we can demonstrate self-similarity in the mean velocity profile by inspection of log law for the grit, but we can't do that from French.
Excuse me. Isn't your wake strength for the smooth channel floor extremely high?
I thought you would put that down. It is quite large, yeah.
What does that come up to a pipe?
Well, we started off with a wake strength of about 3.2, 3.5, and then my co-author revised it upwards. So I haven't met him yet to discuss this. I agree that that's actually quite large, and I suppose here I have to confess that we know that the smooth channel data is not fully developed. So what we did was actually to correct that lack of full development by using this correction from the Melbourne group, where you can take it to be an offset on the log rule for lack of full development. And that actually then gets you back to a smooth constant. In our case, it's 5.4 with the additive constant. Given the kappa that we've got, 0.41, you can think, well, that's actually pretty good, given that we've done this correction. But the wake strength still comes out to be 3.9. That said, even if it were 3.2, I don't think you'd have any problem in seeing that the wake strength has actually gone down really significantly as a result of the roughness. Bit of structure from irregular hot wires. This is eddy chasing at its best or worst. This is over roughly 10 channel heights. Doesn't look as though there are actually really any significant streamwise structures across the span. So this is Z, that's effectively X. If we get a microscope out, well, you might think that there's some sort of low-speed structure here, but it's all really just banged around too much by the roads. No. Now that's in time. What happens if you do the same sort of thing in space? Now we've got a 2-point correlation across the span of the channel as a function of delta Z and delta Y. This is just classic Townsend analysis. So we've got a backflow region, which is indicative of a large roller structure in the XZ plane. In other words, it's somehow elongated in the X direction. And really, the only significant difference between these two is that this angle here is slightly more acute than that one. That's the inclination of the large structure. And you get a length scale. And again, from the Melbourne group, they've actually suggested that a good measure is actually this span-wise width scale, which is not the same thing as a correlation length scale. It's basically the offset going from here to here in units here of delta Z. And how does that look? Well, this comes from Monty's paper. That's probably the best compendium plot that we have. These are the data from the boundary layer. These are the data from the channel. And our data, sorry about this, they all line up along here. So we actually have large roller eddies, which are significantly large, and surely at this size they're carrying a significant part of the shear stress. I think I'm done, really. Question?
I have a 3D.
The idea that the Arnold constant might be the same for smooth and rough soils would apply one which is only for small organisms and not for larger organisms. The idea originally was that it would apply only to small organisms. Maybe I don't even know what's the idea.
Well, we have those concerns as well, which is why we did this sensitivity analysis to this.
I mean, it's not just sensitive, but
Yeah.
maybe you have different.
Well, quite
That
that.
may change the conclusions.
Yeah.
So if you look at the spectrum, you would see very long wavelengths. Which, I mean, it makes sense that these large
Not in time,
oceans
yeah.
are broken up.
It's just broken up.
Actually, for Rocky, I'm wondering when, in your cases where you see the outflow changing, if I remember in your papers, you actually do see the wave decrease in streamline. So we should suggest that if there are long strokes, they're getting broken up by the roughness and stuff. So these are much larger than here you expect it.
We haven't checked out the streamlines extensively at all.
So why do we see this large structure in the atmosphere now?
Well, it's there. This your K and delta is the minus one.
The roughness, the relative
It really
roughness
is
is
not.
tiny.
No, but you also see them in over canopies and other things too.
Yeah. Well, they may be there for different reasons. You get these in the atmosphere. You get there are at least 5 different mechanisms that can produce them. Normally driven by some buoyancy mechanism. So. I'm interested in keeping on schedule. Thank you, Jonathan.